Good morning, everyone. Welcome back. We've been talking recursion, and as I've kind of talked about and shown you, there's no true syntax to recursion. There's only so many facts that I could just give you. There's just so much information I can give you. The real way to kind of learn recursion is to practice it, and we've been doing a lot of that. When we left off yesterday, we were looking at no x given a string, compute recursively a new string where all the x chars have been removed. So we're going to call this method. We're going to pass in some string. In theory, it has some x's. It could just not have x's, such as this second example here. But any x's that are there, they get removed. Okay. So we're going to take in a string, str. We're ultimately going to return a string. We're basically going to consider one character at a time, and then once I've considered it, I'm going to throw it away. And we're going to use basically char at and substring in order to accomplish this. So what that means is eventually, as I'm throwing away characters, I'm eventually going to have nothing in my string. So if the length of our string is 0, that's when we know when we should stop. So if our string length is nothing, we can return either an empty string, we can return str, because it's effectively the same thing, right? Our string at this point is empty. There's nothing there. Okay? So now what we want to do, if we're still in the method, that means that we've got some characters to consider. Let's consider characters at either end. As I've said in like the past 2 lectures or so, that we kind of want to consider things at the beginning of the string because that syntax is just cleaner. Right? So if the first character, that is the char at 0, is an x, notice that we're comparing character to character using an equals relational operator. If the first character is an x, I want to get rid of it. And so what I'm going to do is return an empty string, right? Effectively nothing, the 0 of string, and then put a recursive call to the stack. We'll take our string. I just considered the first character, so I want to get rid of that. So we'll use a substring beginning at index 1, going through the rest of the string. Okay. So if there's nothing left in my string, we just return an empty string. If the first character is an x, I'm going to return an empty string along with our recursive call to no x, getting rid of the first character. If I'm still in the method, what it means is there were characters, or at least one, and that first character is not an x. And so what I want to do is just return the character as it is and keep going. Okay, I think this should work. Yep, we got our green check mark. I do want to kind of look at an alternate approach, which could, it's just an alternate approach. It's not necessarily better, it's not necessarily worse. But if I come in here, I could save the first character. Right? And then I could check the first character. Notice we get a little bit of cleanup there. I can ask, is that first character an x? If so, instead of doing this return statement, the real goal of this approach where I'm including this variable is I have a little bit of duplicate code, right? This call to no x substring, that is the same. The only difference between this return statement and this return statement is what I'm tacking on at the front. And so this attempts to reduce the duplicate code. Not necessarily better, just different. Instead of actually returning in this spot, what I would do was update ch to be nothing. To be nothing. I hope this works. I don't know if there's an empty character for character. And then down here, I'll include ch. Sometimes ch is still the first character when I get down here. However, if ch was an x, it should in theory be an empty character. And again, I don't know if this is actually going to work. Oh, yikes. Empty character literal. That ain't a thing. And if I were to do a space, that's definitely not a thing. All right, my bad. There's probably a way to do an empty character literal. I'll let Twitch chat figure that out. But this is definitely a solution. Is it really an oof? How many people out there actually know that an empty character literal is not a thing? Let's go to the next one. So the stuff that's happening now, we just went through a bunch of string recursion problems. Now we're getting to the point where we're working with some array stuff. And these are kind of fun because as we've seen with each of these, right, we did a bunch on integers. And the quirky thing about integers was using like mod 10 divide 10 to traverse the integer. And then with our string, what we're using is charat and substring. And that is our way that we traverse a string. So we're going to see kind of a quirky thing with our array. And the way that we're going to end up traversing the array is we keep passing the array from call to call. That's how it gets into the method. And then this index is basically I. It's our current position in the array. And so what we're going to be updating with each recursive call is this index. Let's look at our problem. Given an array of ints, compute recursively if the array contains a 6. We'll use the convention of considering only the part of the array that begins at the given index. And this way, a recursive call can pass index plus 1 to move down the array. The initial call will pass index as 0. So each of these calls, we're starting at the very beginning at index 0. And this array is going to stay the same. We're not actually going to edit that. What we're going to change is this index, which is going to be our current position in the array. So all we want to know is, does this array contain a 6? Well, help me out, chat. I need some base cases here. And I say cases with an S because there's some things that you have to consider. All right, we have to consider, is there an X? Or I'm sorry, is there a 6? Right, so one base case is the current element, the one that I'm looking for, is nums at index equal to a 6? If so, I found it, and we're going to return true. That's a base case. I've talked about, though, how we're going to increase this index. This index is going to be updating, and that's how we traverse the array. And so eventually, this could, in theory, right, if I never encounter a 6, right, this doesn't have a 6, I'm worried about this going out of bounds. So another base case here is considering the scenario where what if our index is greater than or equal to nums.length. Okay, this means we would be out of bounds. And notice that I'm checking this first. This is the first thing that we want to check to prevent the future index out of bounds. Right, so if my index is greater than or equal to my length, that means it's not there, so we can return false. We have searched the entire thing. If I'm still here, all we're going to do is return a recursive call to array 6, passing in nums, passing in our index plus 1. So we're going to do the math right here in the recursive call. We'll update index, and the new value is what's getting passed in. Let's try this. This looks like something that we maybe want to trace. Let me see if I can get... Yeah, let's try tracing it with Notepad with like no visual, I guess, or maybe I just plug in an array up top here. We'll use their first example here, 164. I'm going to zoom in on this bad boy. Right, I'm going to let that array just kind of sit up there. That is nums. Okay, so when we first call this, we're going to call array 6. I'm just going to abbreviate that as A, passing in nums, passing in some type of index. In this case, 0 is where we always want to start. We're going to ask, is our index greater than or equal to the length of nums? Well, nums has a length of 3, so that's false. We'll ask, is nums at index currently being 0, a 6? It's not. So we're going to put a recursive call into the stack. We'll have array passing in nums, it hasn't changed, and we'll do index plus 1 or 1. We'll step inside this call. We'll ask, is our index greater than or equal to the length of our array? It is not. We'll ask, is nums at index 1, equal to 6? It is, and so in this case we return true. Okay, let's look at one where maybe we go out of bounds. I believe they do essentially the exact same thing, where they take the same example, yet there's no 6. We'll ask, is index greater than or equal to nums.length? It is not. Is nums at index equal to a 6? It is not. So we're going to put a recursive call in the stack where we'll pass in nums, and we'll do index plus 1. Let's step inside of this call. We'll ask, is our index greater than the length of nums? It is not. Is nums at index equal to a 6? It is not. So we'll put a recursive call in the stack where we do nums 2. We're going to step inside this call. We'll ask, is our index greater than or equal to the length of the array? It is. So we return false. And this false gets passed up if you're curious, right? This evaluates to false, and this evaluates to false, and our final call evaluates to false. How though? You're starting at 0. Yeah. 0, 1. There are 2 indices. The length of this array is 2. Index 0, index 1. I can put some indices up here if you want. Wait, how can index? Oh, index should never actually be greater. Yeah. So I'm getting this question. This I've kind of found is just like good practice is to, we could do this, and it should be the same thing, right? Because I'm only increasing by 1, I should never have a big jump to actually be greater than the length of nums. You are correct in thinking that this is the exact same thing for this particular problem, but this handles more cases. For instance, what if the original index, now I get that these always start at 0, but what if we pass in an original index which is just way out of bounds? Now, this isn't very realistic, and it's maybe something that we would precondition, all those sort of things, but this is also just a very easy thing to implement, right? We're talking the difference of 1 character. And so I've kind of found in practice that when you could just use equals than or equals to, it's kind of better to err on the side of caution and use a greater than or equal to. I do like that question. It took me a moment to figure out what you were asking. Let's go to the next one. Array 11. Given an array of ints, compute recursively the number of times that the value 11 appears in the array. We'll use the convention of considering only the part of the array that blah, 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 blah. Same thing. In this case, I'm not returning a Boolean, I'm returning an integer. We are counting how many times 11 occurs in nums. And we use this index, that's our value of I, that's trying to keep our spot inside of the array. Okay? So, let's go. Base cases. Well, if I'm out of bounds, right? If index is greater than or equal to nums.length, we're out of bounds. We could just return 0 in that case. Right. And the last one, I returned a false value. In theory, if this was like an index of, this would be like a negative value maybe. But we're returning a count overall. And so once I'm out of bounds, we're returning nothing. If the current element, that is nums at index, is equal to the one that I'm looking for, well, in this case, we're going to put a 1 onto this stack because I have found an 11. I want to keep count of it, right? This is slightly different from the last problem because we're counting how many times 11 occurs. So we'll do a 1 plus, and here's my recursive call. I'm going to call array 11, passing the array as it is, no changes, but I've already considered the current element, so I want to increase my index. If I'm still here in the method, what it means is I am not out of bounds. The current element is not an 11. It's something else. So I want to return effectively 0 plus array 11. And again, we're going to keep going. Now, as we've seen from other counts, you don't necessarily have to put this. In the event where you're adding 0, you could just do nothing, right? Okay. Ooh, we got a star. So these are very similar. Again, the little quirky thing here with an array is that we are using this index is getting passed from method to method so that we know what our current position is. Now, what if we just return I don't know what you're typing there. Yeah, okay, yeah, it's not a Boolean. Okay, so per some of our previous coding bats, we see this recursive call that's being repeated. The only thing that's changing is this value here. We could take the approach where maybe we have x that has a value of 0 starting out. If the current element is an 11, instead of returning, I'm going to try to reduce duplicate code, and all I'm going to do is update x. What that means is down here I have one single return statement where I'll just tack on x. Right? A lot of the times x is just 0 and it stays 0. But if the current element is an 11, I'm going to update it to 1 and then we put it here. Again, the only real benefit of this is we're reducing the duplicate code, this recursive call that doesn't change. This is not better, it's just different. Technically, we're taking up extra space because this integer is on the stack, but it's whatever. Ooh, I like this question. Could we just do index plus plus? I'm going to show you. Answer is no, kinda. Okay, so a note on these operators. This is called a postfix operator. What it's going to do is use the current value of index and then increment it. Okay? Whenever this recursive call happens, it's using the current value. So as it stands right now, my index is not changing. It changes after the call has been put onto the stack because it's a postfix operator. Now, some of us it's a super secret tech that I have shown some classes. You're not supposed to know this. College Board doesn't like it when you do this. We can do a prefix notation. What this says is increment, index, then use it. Ta-da! We're going to write a linear search algorithm next, I believe, and a similar thing. And this actually is useful in that context. Sweet. I believe the next one is array 2020 or 220. I'm going to give you that one as homework. I want you to open up the IntelliJ. They won't see it coming. Oh, Firefox does not like my Google Slides. Chrome it is. All right. We did no x, we did array 6, we did array 11. I want to write this method. Write a method indexOf that returns the index in which the specified int, that's this guy, occurs in the specified integer array, that's this guy, -1, if the specified int does not occur. This is going in a class called searcher for a reason. This is linear search. I have a little bit of a peeve. When people talk about linear search in like an abstract context, they're basically saying it should return a Boolean, right? Linear search lets you know if an integer is inside of an array. Yet when we go to write it, we always write it like it's an indexOf type of method, right? It's returning the index at which it occurs. And so people talk about linear search like it's contains and then write it like it's indexOf. Here I'm calling it indexOf because I feel like that's more accurate to what it's doing. I'll get off my stand here in just a moment, but yeah, this is linear search. We're writing in, it's called indexOf, but we're writing the linear search method, and we're going to use recursion in order to do it. So I'm in IntelliJ. I'm going to create a new project. Note that we're calling it searcher. That is because in a future timeline, we're going to be writing binary search. Calling this one searcher. I'm going to expand my project, right click on the SRC, do a new Java class, I'm calling that one searcher. Okay, let's make this go away. So we'll plug in our main method using the PSVM short key. Let's go ahead and get a header here. Now this is going to be interesting, right? We're looking through this array for this integer. Okay, but per the CodingBat problems that we've been working on, this integer here is not something that we're looking for. This integer is an index. So I actually need a third parameter here. I'm going to talk about why I wrote it this way in just a moment, but we actually need a third parameter, another integer, which is our current index. So public static. Ultimately, we're returning an integer, that is the location. We're writing this one's called indexOf. It is effectively a linear search. We're going to use an integer array to kind of demonstrate this. I'm calling that ARR. R. And we need something that we're looking for. I'm calling that key. The last thing I need is an index, and as I've kind of told you, that is essentially I. We called it index. And our CodingBats, I mean, they called it index. It's I. Okay. We're going to return Java docking this bad boy. Let me bump that up some. Return the index at which key occurs in ARR. -1. If it does not occur. Okay. This is linear search. Performs. This is. It's linear search. We're doing it recursively. How about that? So we could label these things. You know, R is what we're searching through, key is what we're searching for, and I is the current index if you really want to go that extra distance. Let's get started. Base cases. Similar to our CodingBat, we're going to be incrementing this index, I. Eventually, it could go out of bounds. So that's really what I want to check first before I check anything else. If I is greater than or equal to ARR dot length, that means we're out of bounds. I want to return a -1. If we're out of bounds, that means we never found it. If the current element is what I'm looking for, however, we can just stop there. So if ARR at I is equal to key, this means I found it and it's at the current index. I'm going to return the current index. Yes, this is just a loop. So that's kind of the point. Recursion is an alternative to iteration. I wouldn't write linear search this way. We've written several linear searches using iteration, using loops, for each loops, and they're cleaner and more efficient than this, and probably more intuitive to you. that tends to be people's peeves with recursion, especially at this level. That's one of my peeves with recursion. I don't honestly think we should be teaching it. It is, however, kind of good to see it, because in the event that you come across it, for instance, with merge sort, which by the way, for CSA, you do need to know those searching algorithms, the sorting algorithms that we talked about in CSP. We'll be kind of reviewing those. In particular, binary search I'm going to hit in our next lecture. In the case of merge sort, the recursive solution is actually the prettier one, is the cleaner one, the more elegant one. And so that's the one that everyone uses. You can write an iterative solution to merge sort. It's a hot mess. So if you were to come across that at any point in your computer science career and you're just like, whoa, this method is calling itself, and you have no idea what recursion is, then yes, I could see that kind of warrants teaching it this early. We're going to get to Towers of Hanoi next week. I have the quintessential problem that should be written recursively. As it turns out, this is like spoilers, but sorry, lost my train of thought. There are certain problems in which the recursive solution is elegant. Merge sort being one of those. And that's why you ultimately want it. That's its real advantage over iteration. And I'll show you. Like, you're just like, how much better could it be? But when you see an iterative solution to merge sort, you're like, ugh, that's disgusting. And then it kind of makes sense why recursion exists. I mean, it didn't have to, but here we are. Okay. If I'm out of bounds, we're going to return a -1. If the current element is the one I'm looking for, we're going to return the current index because I found it. Otherwise, we need to return indexOf. We're going to keep doing our search. I'm not changing the array. I'm not changing what I'm looking for. What I am going to change is I, right? I is going to be one more than what it was. Let's try this out. And as you're going to see, we could use prefix orientation here. Notation. I'm going to hop back up to my main method. Give me some numbers in chat. I already know what they are. And we're going to fill up an array using an initializer list. 3, 7, 42, 50. Oh, thank you. 6, 9, 420, 666. These don't have to be in order. I'm putting them in order just because I can. So let's do indexOf. This method needs an array to search through. It needs something to search for. Why don't we search for 42? And we need a place to start. Index 0. Now, IntelliJ's yelling at me because this is returning a value. That's the information that I want. We need to print that off. So I'm going to sout on this. I'm going to right click in free space and tell it to run. And index 2, 0, 1, 2. Yeah, it's not there. Okay, what if we were to search for 404? -1. Not found. Okay. So, real quick aside. The original method header I gave you didn't have the integer index. Okay? That is because whenever we perform indexOf, we're like always going to put 0 here. Like in practice, that's what's going to happen. Something we can do is, there's probably a term for this, but write some type of starter method. Right? I'm going to write an indexOf that takes in an array, and it takes in what we're looking for, and that's it. I'm overloading indexOf, and all this is going to do is call my other indexOf, passing in the array that I'm looking through, what I'm looking for, in index 0. The whole point of this little method is so that I can clean up this syntax. Right? Now I can call indexOf. I don't have to provide the initial 0 because it's kind of silly. Of course, if we're going to search through an array, I'm always going to start at the beginning. So why even have that there? So the only reason this exists is to clean this up, and all it's actually doing is calling indexOf, providing this 0. So we get something that's a little bit cleaner on this end, but in terms of the actual recursion, I need that parameter to exist. So this one is the one that's actually doing all the work. There's probably a name for this. I'm just calling it a starter method. Okay, that's going to wrap us up today, guys. And if you would, do array 220 under the recursion 1. Send me your solutions via Discord if you got something that you're proud of. Let's chill.